Hello world, it's Sumit. So in today's session we're going to talk about evaluation metric, which we often call as a loss function. And this evaluation metric, it can be only applied for the regression model, like what kind of algorithm do fall under this regression model, we can apply this evaluation metric. So I'll recommend you to watch one video, like that would be the first video of this playlist, so that you can get in depth knowledge about like what kind of algorithm do fall under this regression model. So before moving ahead, I'm going to give you a brief outline of what we're going to cover up in today's session. First would be like what is the evaluation metric, where we're going to discuss about the different types of it and what's the use of it. Then we're going to move on to understanding the type of it, like what is mean square error. We're going to understand that as well as mathematically, like how we can solve it in a similar fashion. We're going to do it for the r square as well. We're going to see that theoretically and mathematically, like how does it behave, and then we're going to compare both of it, like mean square and r square, visually by plotting that in a 2D graph to understand in a more At last, we're going to jump into the code snippet. We're going to see like how we can call different scikit-learn APIs to call different types of evaluation metric to evaluate our model. So let's move ahead. So very first thing is knowing about like what is evaluation matrices for regression model. And evaluation metric is nothing just a technique that is used to judge the performance of your model. For example, you go and give up any exam against your skill set, and at last they will going to publish the result evaluating the performance of you, like how well you had performed in that particular exam. So that is just to evaluate you, like how you are good at that particular skill set. In a similar fashion, evaluation metric is nothing just an technique which judges the performance of a model, and it has been oftenly called as a loss function. And result from this what you get from evaluation, it used to benchmark accuracy of your model over any trained data set. So next is like types of evaluation matrices. So there are basically four different types. First is mean absolute error, mean square error, root square error, and r square error. So we're going to talk about this in very detail, and we are going to see mathematically like how we can find them, and why, like in Python, how we're going to call this. So let's move ahead. So the very first type of evaluation metric is mean square error, which we're going to discuss about. And for this, like mean square error basically tells you about like how close your regression line is to the set of the points. And how do we get the regression line? That is like based on your predicted values over any data set. For example, in this plot, if you're going to see it, this red data points indicate the predicted value of y, whereas this green points indicate the actual value. So against each of the actual value, there is a predicted value, and there is a overlap of like actual value and the predicted value. And once you get the predicted value, you can draw a kind of best fit regression line across it, and you can find out like how close your actual value is been with the predicted value. Meaning the smaller the number of error, the more accurate you, the smaller it is, the closer you are about to find the line of best fit line. So let's see like how we can find mathematically like mean square error. Let's say I have xy values with me, which I can plot that in a 2D graph, and against each of the y value, which is my dependent variable. For this, I have my independent variable, which we can say as an x. I have the predicted value against y is like yp, which we're going to say as the predicted value against each of the y value, actual value. You can say like for this 3 we have got 2.8, for this 4 we have got a 3.2. In a similar fashion for all, like for this 5 we got 4.4. So once you have to plot this in a 2D diagram, it will going to look like this, where this red dots will going to denote the predicted value, whereas this green dot will going to denote the actual value. So now we know the formula for this calculating the mean square error is like 1 by n summation of y minus yp of whole square. So we had this y and yp with us. We just need to subtract the values and do a whole square of it. So if you're going to do a subtraction of y minus yp against each of the cell of this values, you're going to get the values as 3 minus 2.8, that is 0.2, and once you need to get for all the values against all the data set, which you need to calculate the distance between each of the value, like this for this predicted value and the actual value, the difference between them, the difference between this in a similar way for everything. For this 4 you can see this is 0 because this actual and the predicted value has been overlapping with each other. So now you have to do a whole square of it. Doing the whole square of it, you will going to get the values of this y minus yp. Now to get the summation of it, once you're going to get the summation as 3.6, adding up everything, then we're going to put that in a formula to get like how we can calculate this MSC. Then next would be like 3.6 divided by 5, and 5 would be the number of the data points we have. So for this 3.6 by 5, it would be give me around 0.72. So that would be my mean square error. So this way mathematically we can calculate the mean square error, and we get, but in the while doing the coding we just need to call the APIs. But to understand that in a mathematical way what is mean square error and how we used and how we have to calculate it, so this is a very simple formula which we used to put out everything and we used to calculate like this. So basically mean square error talks about the distance between the actual value and the predicted value. So now moving ahead. So next is root mean square error. So how we had calculated this mean square error, the same way we're going to calculate for this root mean square error. So for this as well, if I want to get the data points as xy, where y is my actual value, and against each of the actual value I got the predicted value as y, and we're going to plot that in a 2D diagram. So once we're going to plot it, so now we know the formula of this root mean square error is like root over summation of yp minus y, which is like yp denotes my predicted value minus actual value of whole square by n minus 2. So in a similar way, we're going to find the difference between yp minus y against each of the data points. That would be something like this, like yp minus y. I have already calculated that before. So the next would be like doing the whole square of it and summation. So once we're going to do a whole square of it, we're going to get something like this, squaring up of this, because this will going to remove all the negative value and it will going to add more weights to your model. So once you need to do yp minus y of whole square, then at last we need to do a summation of it to put out, and we got as 3.6. Now we're going to put that value in the formula to calculate the actual root. So that would be like under root 3.6 by 5 minus 2, where 5 is the number of the data point. For example, in this case I have only 5 data points, 1 2 3 4 5. So 5 minus 2, that would be 3. This would be giving as around root over of 1.2, that would be 1.09. So we got the root mean square error as 1.09. So this way we calculate the root mean square error, and it's very simple formula like this mathematically how we can calculate this. So with just the performance of your model, so we got to know two things, like first thing was mean square error, other thing was root mean square error. So now we're going to move ahead and we're going to see about talk. So before moving ahead and understanding mathematically like how does R square error behave, first we want to understand that in a very theoretical way, like because it would be little different from mean square error and root mean square error what we had already discussed about it. So in this R square error, R square is just a statistical measure, like how it's the one type of the evaluation metric we had already know about it, but it talks about in a very different way, saying about in this R square we always need to calculate the mean of against the y, and against the y we need to compare the distance between the actual value and the distance between the predicted value. For example, in this 2D plot diagram, this red points as usual it denotes the predicted value, whereas this green point denotes the actual value. So now to calculate the R square, we need to compare the distance. We need to calculate the mean of it against the y, the dependent variable which we are already predicting it, and against the predicted. Once we need to calculate the mean, we will need to compare the distance between this actual value and the mean, and distance between this predicted value and the mean. So we're going to talk about this in detail, but R square does not indicate whether the regression model is adequate or not, and you can have low R square for very good value, indicating the higher the value, like it's more nearer to 1 or it mostly ranges between 0 to 1, and it's more nearer to the 1. It's like more these data points have been near to this line of regression line. So now we need to understand that mathematically, like how we can calculate r square. Let's say I have x and y with me, which we're going to plot that in a 2D diagram against this predicted value. So once we're going to calculate this, we're going to get the predicted value and we're going to draw a regression line across it. So once we draw the regression line, we know the formula of this r square, that is summation of yp minus y bar, and this y bar denotes the mean. And whereas by summation of y minus y bar actual value, we calculated the mean, which came around 3.6, and we had drawn the line across this 3.6, which with the mean against the y. So now would be putting that in the formula, as we'll first going to calculate yp minus y bar and y minus y bar. So first would be yp minus y bar or y minus y bar. For y minus y bar, that would be against each of this 3 minus 3.6, that is minus 0.6. In a similar way, we're going to calculate against each of this data cell. That would be for this 5, this 5 minus 3, this is 5 minus 3.6, that we're going to do a whole square of it. That would be the whole square, and doing this whole square will remove all the negative sign as well. In a similar way, we're going to do it for the yp minus y bar. That would be, we're going to calculate the summation of it to put this across here, 5.2. And for this yp minus y bar, we have yp minus y bar. Yp minus y bar, this 2.8 minus 3.6, that would be minus 0.8. In the same way for all the data points. Now we're going to do is whole square of it, which came around 0.664, which we're going to do a whole square of it. Now at last, so once we got as 1.6, now we're going to put that, once we calculate everything, now we're going to put that in a equation to get it. Like we got around 1.6 by 5.2, that is 1.6 is my summation of yp minus y bar, yp minus y bar of whole square, and y minus y bar of whole square, which is 5.2. So we got the r square as 0.37, which is very low. If you want to take up this data set, you will want to see this is my predicted value and this is my actual value. We have calculated the distance between the actual value and the mean. Now we had calculated the value of the r square, which we often call as the godness of fit. To see that in visually in 2D plot diagram, how does that behave, the value of r square affect the accuracy of your model. Let's say I got at around r square as 0.37 against my data set, and this would be my actual value. Against each of the actual value, I got the predicted value, which we're going to plot like this and create a regression line across it. Now if you're going to increase the value of the r square, let's say as 0.67, then in that case the value, the actual value which are there, it will going to come closer to the predicted value. And the more, if you're going to increase the value of this as r square as 1, the more closer it will going to come to your predicted value, meaning the value of the r square ranges lies between 0 to 1, and more it is nearer to 1, the more nearer your actual and predicted value would be. And the lesser the value of this, the more could be the number of outlier present in your data set. So this is how r square affect the accuracy of the model. Next would be, we're going to compare that visually, like the difference between the mean square and the r square, what we have understood till now. First would be the mean square. So in mean square, we have seen, once we're going to plot the 2D diagram of our actual value and the predicted value, we just create a regression line across it, and once we draw the regression line across it, we have to just calculate the difference between the actual value and the predicted value, meaning where would be lying the actual value and the predicted value, we just calculate the difference of the length between each of it to compare the accuracy of the model. But whereas in r square, we do it in kind of different way. We plot the 2D diagram and get the regression line, then we calculate the mean of it, of the dependent variable. Once we draw the mean, then we compare the distance of it. First we want to calculate the distance between of mean and the predicted value, then we want to calculate the difference between the actual value and predicted value. So this way we compare the distance between actual value and the mean value with respect to the mean. So that's the major difference between mean square and R square. I hope I had made myself very clear on this, like the very difference of it, to visualize and see like how we can see the difference between them. So next would be the code snippet, like how does it behave. So in our code, if we're going to, this we're going to discuss in very detail once we're going to start with the coding session. But till then, let me tell you this, we can simply use the scikit library. From the sklearn, we can simply import matrices, which would be one library, and in the in that matrices there are certain APIs like mean absolute error, mean square error, square RT, R square score, which this would be R square. And in all of this we used to pass our white test data and the predicted value. This would be my unseen data, or the test data, you can say. Against each of the test data we pass a predicted value, which we got the predicted from our model. So we just to pass this and we get the value of it. We're going to discuss in very detail how you can minimize or increase the value of it to best fit your model. Okay, to summarize up, like wrapping up everything, like what we had learned. First, we saw the like what is evolution matrices for the regression model and the different types of it. Then we move on to understanding like what is mean square error, the first one of it. Then where we saw mathematically how we can actually calculate it. Then we got to know about like R square, in the same way we calculate it mathematically, like how we can calculate that. Then we compare both of them visually, like how we can calculate or how we can visualize to understand like how does both behave. And at last we jump on to see the code snippet in actual environment, like how does we call and get the values of it, all the values of the matrices, to know about like how well our model is performing. I hope you had liked the way I had explained, and if you had really liked it, please do like, share and subscribe Cuplo on my YouTube channel, and please give your valuable feedback through comments, which will going to help me improving my video. And please hit the bell notification icon for any new video update so you don't miss any new video update on my channel. So till then, thank you all.